Carlos, it's really my pleasure today to have you do this Blackboard talk for us. I really look forward to hearing what you have to say. So with no further ado, I'm going to hand it over to you to tell us what's up in Precision 21.
Okay, thank you very much for this invitation. So then I think I apologize that this will not be a real Blackboard talk. Will be more a colloquium talk that will cover several topics and will focus a little bit on the topics that we cover during the workshop. So as Lars was saying, I will talk about precision measurements in the high luminosity LHC era, and for that I need to introduce a little bit the elements with which we are going to work. The first one is the standard model. As you probably well know, is an extremely successful theory. Describes all interactions between the known elementary particles apart from gravity. And it consists of 3 generations of fermions, what we call matter, that are composed. The first generation is just the up and down quarters for protons and neutrons, and the electrons and neutrinos. They come in 3 generations that differentiate themselves only by their mass. So I mean, for the up quark, we have a partner, that second generation partner, that is Cham quark, that is somewhat heavier than the up quark, and the top quark, that is the heaviest particle we have observed, that weighs about 175 times the mass of the proton. So, and the same happens with all the other particles that we know. For instance, the electron comes with a cousin that is called the muon, that is will play some role during this talk, and a heavier one that is the tau lepton that has a mass close to the proton mass. So these particles interact via forces that are mediated by gauge bosons similar to a photon. So they are gluons, the carriers of the strong interactions that glue together the quarks inside the protons and neutrons, for instance, and they are the weak interactions that I will describe a bit in detail later. And also we have the Higgs boson that will play a very important role in this talk and has played a very important role in our workshop. So let me remind you about the weak interactions. The weak interactions are those interactions that mediate, for instance, the beta decay of a neutron into a proton, an electron, and an antineutrino. They are mediated by these heavy gauge bosons. The mass of these heavy gauge bosons is about 80 times the proton mass, and are described at low energies by the so-called 4 Fermi interaction. So like a point interaction where you don't see the gauge boson at low energies and only manifests itself when you go to sufficiently large energies. Now that this is not unique to the neutron, any other heavy particle that belongs to the second and third generation that I was describing, so will decay via the weak interactions into lighter generation particles. For instance, that is the case with the top quark, so that decays into a bottom quark mostly, and for instance, a positron and a neutrino, or can decay into jets, so that are forms of quarks. So that also happens with the muon decay, that is well known. The muon decays into electron, neutrino, and antineutrino, and is mediated by the same process, then with a characteristic interaction that is the so-called G-Fermi. So that is a massive interaction constant that I will describe in some detail later. So apart from these charge interactions that mediate decays, there are also neutral interactions. Those do not mediate decays, but are very important for the behavior of the weak interactions as a whole. So apart from that, of course, there are the electromagnetic interactions inside the standard model, and finally the strong interactions, as we were saying, those that glue the quarks together inside hadrons. And they have been tested both perturbatively and non-perturbatively. Perturbatively, we know that these interactions become strong at scales of about 500 MeV. So there where the validity of perturbation theory stops And we have to carry out non-perturbative calculations to really study the predictions of these interactions. For instance, the spectrum of mesons that is induced by these interactions can be studied by doing a path integral quantization of QCD in the so-called lattice simulations. And you can see in this plot on the right a comparison between the predictions that come from the lattice simulations and observation, and you see that there is excellent agreement. We also see here a behavior of the perturbative behavior of the interaction constant, the so-called alpha strong, that is similar to the value of alpha electromagnetic, but now for the strong interaction constant. And they have this characteristic behavior that becomes weaker and weaker as the energy raises, and this is a famous property of asymptotic freedom for which Wilczek and Gross and Pulitzer won the Nobel Prize not long ago. Now, all these interactions can be tested very precisely and at different levels of precision, and let me just tell you something that is quite important. For instance, the precision test of QED associated with the measurement of G minus 2. So as you know, the precession frequency of a lepton spin in a magnetic field is controlled by a so-called G factor that is approximately equal to 2, that controls the precession frequency as a function of the magnetic field, the charge, and the mass of the particle, an expression that I'm presenting here. Here, the gamma factor is simply a relativity factor. So then now, when you can compare this precession frequency of a spin in a magnetic field with the cycle frequency that is regulates the rotation frequency of a charged particle in a magnetic field, that is given by a similar expression, but lacks this second factor that depends on G. So therefore, if you make the difference between the precession factor of the spin in a magnetic field with the cyclotron frequency, so this difference is directly controlled by the ratio of the product of the charge, the magnetic field, to the mass of the particle, and directly proportional to this factor G minus 2 over 2. So therefore, if G would be exactly 2, like it would appear naively from the Dirac equation, so you would see that the precession and cycle frequency would be equal, and therefore when the particle turns around, the spin at every turn will point in the same direction. However, if G is slightly different from 2, that will not longer happen, and you will see a slight variation of direction of spin with respect, for instance, to the momentum of the particle, and that is regulated precisely by this difference G minus 2, because it's the one that controls the difference between these two frequencies. Now, it was noticed by Schwinger, so that when you perform quantum corrections in the case of QED, the value of G is no longer equal to 2, but acquires a small difference, and the difference between G and 2 over 2 is controlled by alpha. It's equal to alpha over 2 pi. And today we know that this is just a property of the first quantum corrections that you can perform, but the QED corrections can be performed to higher degrees of accuracy, so in higher orders of perturbation theory. And today we know the deviations of G minus 2 computed up to fifth order of perturbation theory. And just to give you a representation of how the phi loop contributions look like, you can see that it's an extremely complex calculation that is very demanding computationally, and only a few groups have the capabilities of performing these calculations. But today we know the difference, the value of the so-called anomalous magnetic moment of the electron or the muon, the contribution, the QED contribution that is formed by photon loops and charged lepton loops, so loops of electrons, muons, or taus, to an explicit degree of precision. You see that we know the value with many significant digits, and the error is in these 3 digits. So therefore, we know the value of order of 10 to minus 11 with the error that exists in the last 3 digits. So then and this can be compared with data. Now, amazingly enough, we need this level of precision to compare with data, and this has been done. So to compare with data, we need to have an independent measurement of alpha, of the electromagnetic constant, and this can be determined by atomic physics experiments. And you can perform, therefore, you can use that value of alpha that you obtain from atomic physics experiments to compute G-2 theoretically, and compare it with the value of G-2 that you can compute experimentally. And when you perform this comparison, you see that the difference between the experimental value and the standard model prediction is at the level of 10 to minus 12. And actually, so if you consider two different measurements of the electromagnetic constant, you see that if you average them, you find excellent prediction of the anomalous magnetic moment computed experimentally and theoretically at the level of 1 times 10 to minus 12. So that I believe is one of the more fantastic successful comparisons between theory and experiment. So therefore, this works very well. Now the muon.
Sorry,
yes.
Can I ask a question? I should know this, but well, when you quote the result for the calculation, why do we have why is the error quoted in so many different parentheses? What does this mean?
Yeah, there are errors, there are parametric errors, there are systematic errors, there are statistical errors. So okay. I don't remember the order of these, but there are several different errors that enter in this calculation. So then errors associated with the measurement of alpha, errors statistical, errors systematic of the experiment itself, and all those.
But then should I actually think of adding all these errors in quadrature to be, completely conservative? Or
yeah, the combination of errors is an art, as you know, and in particular when you deal with systematic errors. Then I trust that this combination was performed well. Then I cannot judge it.
But so do the round brackets mean something different to the square brackets?
Right, the square bracket is a combination of them.
I see. Okay, so that's what you meant.
So and has been combined, as you can see, in quadratures.
Okay. Yes.
The 100 dominates the whole thing, and then the other things make small corrections to it. Yeah.
Okay. Thank you.
But the agreement will be equally impressive if you combine them linearly. Yeah.
Sure. It's just I saw this many times, and I always postponed looking into what.
Yeah.
What I mean.
But you see, this is incredible, right? Incredible amount of. First, the precision of the calculations, the precision of the experiment, and the comparison, the fact that they agree so well. So for a while, the first measurement that is presented here caused some question that maybe we were seeing a deviation with, associated with new physics. But as you see, then there was a second measurement that the central rays on the other side. So these are extremely delicate experiments. So it's one should wait for confirmation of these measurements. And if you average, these are two independent determinations of alpha compared with G-2, and you see that if you combine them, you essentially obtain perfect agreement with the experiment. So then, but still, it could be that there is new physics, but nothing here tells us certainly that there is new physics. A different story happens with the muon G-2.
By the way, Carlos, I think there's a more recent measurement.
No, this is this.
Sorry.
This is a Saclay measurement, and this is a Berkeley measurement.
Great, the Saclay one.
These are two independent measurements, and they point in different directions, but you see, that is precisely what,
you're right.
That is what I tried to explain. So anyway, so this is an interesting story, but we haven't come to an end. Then there's the question of the muon G-2 factor. Here the story is a little bit different because the muon is a heavier cousin of the electron, and the mass of the muon is 200 times the mass of the electron. And this is very important because the correction of heavy particles to the anomalous magnetic moment tend to be proportional to the ratio of the mass of the lepton, here the electron of the muon, to the mass of the heavy particle square. So, and therefore, then the correction, for instance, of weak interactions or heavy mesons in QCD tend to be suppressed by a factor 40,000 for the case of the electron compared to the case of the muon. And therefore, then, and the same happens if we have new physics associated with heavy particles. We'll follow this rule. Now, the weak interaction corrections associated with heavy particles to the anomalous magnetic moment muon have been computed, and the error in it is of order of 10 to minus 11, so very small error. The so-called lie-by-lie contribution of heavy mesons has also been computed. Here the errors are a little bit larger, of order 20 times 10 to minus 11, but there are different computations based on theoretical models, based on dispersion relations, and based on lattice calculations. They all agree that the value is essentially of order 10 to minus 9, with an error that is about 10 to 20% of it. So again, these are...
Carlos, I would not agree with this. But I think it is too much optimistic. So because it's very much subjective.
But you were part of this theoretical agreement.
But I was a part which did not agree with them.
Very good. Okay, so let me say it in a different way so that you would agree. So there are three different determinations, all of them somewhat imprecise, all of them give the same sign, and then the mean value is within the errors that I'm quoting here. So, but this will not have a major impact in what in the story I will tell you.
No, but the reason, Carlos, I mentioned that if you ask me, could it be twice as large? I would say it's possible.
I see. Nothing indicates that it's twice as large in the
No, but it is model dependent statement. No, look, I mean, it's not that I'm. Look, for example, our value was somewhat larger than this, maybe 140 or whatever. But you see, it's just I'm trying to characterize the reason uncertainty there.
Arkady, are you saying the twice as large the value or the
value? He means the value.
No. I mean, okay, you can say that. You can attribute it to saying that the error is larger, but our value was larger, right?
Right. Okay, so then good to know, Arkady. I thought that there was already a theoretical consensus that the value had to be about what I'm presenting here, because there are three different estimates and all of them give values, but I didn't know that there was people like you who disagree with this statement. So you never raise your voice saying this in the presentations that you share with me. Okay, anyway, so then if it were twice as large, it would have an impact in what I'm going to say. So if the error will be inflated somewhat, will not. As you see, what the present discrepancy that you probably heard about between theory and experience is about 250 times 10 to minus 11. So if this value will be raised by a factor 2, that will have a serious impact. But as I said, so far as I know, nothing indicates that, but we can discuss that later. Then there is this important hadronic contributions. These are vacuum polarization contributions that are computed right now by using hadronic cross-sections and dispersion relations, so essentially the optical theorem. And then the hadronic cross-sections are E plus E minus going to hadrons. And here I summarize so different results for the hadronic cross-section and a certain range of energies that is relevant for this. And you see that there is a certain dispersion between the hadronic cross-section values. This dispersion has been taken into account in the final result as some sort of systematic error. So, and let me And then it was compared, so the predicted values, the sum of all these contributions, was compared to the measurement at the G-2 experimental formula. That essentially, as I said, measured the spin precession in a uniform magnetic field in a very delicate way. Now, this is the result that has been advertised. So there is a difference between the experimental value. The difference existed already in a previous experiment, the so-called Brookhaven experiment, and has been somewhat confirmed by the Fermi results. So the average, if you trust the theoretical and experimental errors, is about 4.2 sigma away. And as I said, most of the errors that appear here, so in the theoretical prediction, come from these hadronic vacuum polarization corrections. Now, as I said, the errors associated with lie-by-lie contribution that Arkady was mentioning is that I use is about 20 times 10 to minus 11. This comes from a study, a theoretical study that I think I quote at some point, but as I said, then this here it is. So this is the theoretical study that you can take a look at. So tens of theories gathered together to estimate what is the theoretical prediction. So I assume that this is a precise theoretical prediction, but I will comment on it later. So in that sense, this error, so 43, is associated with experiment, in the sense that the way that we use the hadronic cross-section and we convert them into a prediction to AMU. So therefore, in a sense, the current discrepancy is between the experimental determination of G-2, that is supported by Brookhaven formula, and the plus and minus hadronic cross-section data. All other factors, modulo de comment by Arkady, are under good control and the certainties are small. The good news is that the G-2 collaboration will reduce the error of factor 2 by hopefully next summer, and there will be further work on the hadronic cross-sections and theoretical estimates. And if the discrepancy persists, there are many new physics explanations. All of them fulfill this golden rule that you put something heavy and then the corrections are proportional to ratios of ml over heavy squared. So therefore, if you want to have a correction as large as the one we observed, the new particle cannot be very heavy. That is a very important thing. So then, and that you guess it from the fact that if you take couplings of order 1, like the weak couplings 0.6, so then the corrections that the gauge bosons induce are of the order of the current discrepancy. So therefore, you cannot make the particles extremely heavy. So, or if you do it, you have to crank up the couplings to very large values. So now.
But it is, I'm sorry, Carlos, to interrupt, but it is implying that you still preserve this helicity of, chirality of muon in the interaction, right? In principle, you can invent, It
could be, I agree. Okay, those are details. Then, generically, what I said is true. Then the comparison, however, of an independent calculation of hadronic polarization contributions based on lattice gauge theory, similar to this path integral quantization that I told you about, that computes the current correlations in QED, then and the QCD effects on it. So then leads to a value that is somewhat different from the one that we extract from the hadronic cross sections. So, and as you see, if we trust this lattice computation, that is in principle a first principle derivation of these contributions, then the discrepancy will be small. There will be, however, a discrepancy between the hadronic cross-section data and the one that you could extract by reverse engineering the hadronic vacuum polarization from the lattice calculation, and we still don't understand what is the source of this difference there. So we expect this picture to be clarified within the next 2 years by new lattice computation, theoretical analysis, and new experimental results. So then one should stay tuned and wait to see what happens. Okay, there are other precision measurements. The electronic sector has been precisely tested by measurements essentially associated with the decays of the Z boson and also the masses of the W and Z gauge bosons that acquire quantum corrections. Now, there are the so-called oblique corrections that are associated essentially to vacuum polarization effects to the W and Z boson propagations, and are important because they control universally all the couplings of these gauge bosons to fermions, and also they control their masses. And one can organize all this information in a few parameters that contain all the relevant information associated with vacuum polarizations, with these so-called oblique corrections. And there is a very important parameter that is I define here, that is called T parameter, based on the definition of this gentleman, that has the property that is quadratically dependent on the torquear mass. So if you vary the torquear mass, it will move in a dramatic way, and logarithmically dependent on the Higgs mass. So therefore, then one could use this information to compare the values of these parameters to the implications that these parameters have on the precision electrolytic observers, that are essentially the values associated, the masses, the width of the particles, and the cross sections of the particles associated with the couplings of the H boson, the Z gauge boson to fermions. And you can by the comparison, get an accurate determination of what the torquear mass should be, independently of the direct measurement of the torquear mass, and then you can compare it. Actually, from this comparison, we were able to predict essentially the range of torquear masses in a somewhat inaccurate way, but here I show you the predictions of the torquear mass through the years before the torquear mass was measured, based on this kind of experiments of precision observers. And you see that although we didn't know the exact value of the torquear mass, we knew that the torquear mass had to exist and had to behave, say, that 100 GeV. And by the time that it was measured, then we knew that the torquear mass has to behave at about 150 GeV and below about 200 GeV. So the fact that the torquear mass ended being 175 GeV was not a big surprise. Now, on the other hand, these calculations assume that the standard model is valid, that there is nothing that is affecting the standard model. So all the predictions are within the standard model, and no new physics is affecting these oblique parameters, if you will. So, and that is not necessarily true, but what the agreement between the observation and the predicted value of the torquear mass from precision observers tell us that if there is new physics, they should have small effect on these precision observers. And here is a comparison of the measured value, for instance, of the W mass and the torquear mass. This gray area is the prediction that you will obtain based on these precision electrolytic observers, that a measurement of MW can be associated via this prediction electrolytic observers on a certain range of value of the torquear mass. So, and this is the values that you would obtain from a fit of the precision observers. These lines, that are diagonal lines, are the evaluation of the logarithmic dependence that characterize the logarithmic dependence on the Higgs mass. And if you put everything together, then you see this correlation between the torquear mass and the W mass, and by this very thin ellipse that is associated with the values of the Higgs mass that we measure. And this has to be compared with the ring measurement, and you see that there is an excellent agreement between the value that we measure directly for W on the top and the value that we infer from precision observers. Now, the torquear mass, as I said, has been discovered, was discovered at Tevatron in the year 1995. And with that, we let the door open for the Higgs boson. Now, the Higgs boson is a particle that's associated with so-called Higgs mechanism, that is the mechanism through which the particles acquire mass, all elementary particles we know. So then, for instance, it is known that we cannot give bare masses to fermions due to the fact that the symmetries of the standard model, the gauge symmetry of the standard model, are such that only left-handed particles interact via the weak interaction. So therefore, left-handed fields transform the weak interaction symmetries, but the right-handed fields do not. And then this particular operator, psi right bar, psi left, that is the mass operator, would not be invariant. To make it invariant, you have to introduce an additional field, the so-called Higgs field. So, and the Higgs field transform the weak interaction in such a way that to make this invariant. Now, the interesting thing is that when you do this, then if the Higgs acquire a back expectation value, like the one that I'm describing here, so all the masses of fermions become proportional to the back expectation value of Higgs field and directly proportional to the coupling of these particles to the Higgs. So for instance, the top quark mass is very heavy simply because the coupling of the top to the Higgs is of order 1, and the electron is very light in that sense because the coupling of the electron to the Higgs is of order of 10 to the minus 5. So that is the explanation that we get from the standard model to the hierarchy of masses is associated with hierarchy of couplings of the particles to the Higgs. Now, these Yukawa couplings are arbitrary, so then we have to simply are set by comparison with experiment, but there are other relations that are set in stone. For instance, the W mass is proportional to the back expectation value of the Higgs, but proportional to the gauge interactions that associated with the weak interactions. And the Z mass, this neutral heavy particle, so has also a similar relation, but the constant of proportionality is the square root of the sum of the squares of the weak interaction coupling and the hypercharge coupling, while the photon and the gluon remain massless. Now, the Higgs mechanism then has also associated the fluctuations in the radial direction of the Higgs. So they are, when you break spontaneously the symmetry, there are 3 Goldstone modes that appear that form the longitudinal components of the W and Z bosons in the usual Higgs mechanism. So, but there is also a radial mode that's associated with quantum fluctuations in that direction that acquires mass, and that is what we call the Higgs boson. The Higgs boson is essentially associated with the fluctuations of the Higgs field in the radial direction, and acquires a mass that is proportional to another arbitrary parameter, that is the quartic coupling of the Higgs potential, and is essentially 2 times the quartic coupling times the square is the Higgs mass square. From there, we infer that the quartic coupling in this picture should be of order 0.125, because the Higgs mass is about 125, and the back expectation value is 246. Now, I have to say a few words on flavor physics and scales that also is associated with precision measurements. In the standard model, heavier fermion particles are said against to lighter ones via the weak interactions. Now, there are 4 Fermi interactions that one can describe by integrating out the heavy particles, essentially the propagator of this particle. So then can be, the momentum dependence can be ignored, and you have a point-like interaction. This point-like interaction is simply so associated with 1 over the mass of the gauge Monson square from the propagator times the coupling G2 square. And since the mass of W square is proportional to G2 square, essentially the 4 Fermi interaction, or the 4 Fermi constant, is secretly equal to 1 of the back expectation value of the Higgs square. So Fermi proposed this constant in phase 32. Do you know anything about the Higgs? But if you look at it, it's nothing but 1 over the square in the modern version. And induce this so-called 4 Fermi interactions between the muon, the electron, and neutrinos. Now, there's another issue here, is that when you put the Yukawa couplings multiplied by Higgs, you have 3 generations, as I said, and then you get a 3 by 3 mass matrix associated that is arbitrary in generation space. Now, the W coupling is not really diagonal in generation space, because although then associate up and down quarks, and therefore will be affected by the associated rotations when you go from the weak interaction basis where these interactions are diagonal to the mass basis. Essentially, there is a unitary rotation matrix that is associated with the relative rotations of the up and down quarks that appear in the vertex. So in each vertex will appear the matrix elements of these interactions. So when you consider the transformation of a down on a quark. So then these matrix elements are approximately equal to 1 for a given generation, but they are off-diagonal elements that are small but are important. And they're very important because they mediate, they end up mediating flavor transformations. And the mechanism that we use to describe them is a mechanism based on these four Fermi interactions, similar to the interactions that describe the case of the muon into an electron and neutrinos. So you can describe also transitions of mesons, for instance, the K meson that is a composite state of the down quark and its cousin, the strange quark. It can decay into a pion that mediates the nuclear forces and two neutrinos. So, and the way that we describe this is by using the formalism that is based on four Fermi interactions. Now, this secretly, then if you look at it in detail, instead of four Fermi interactions, are associated with mediation with the interchange of gauge boson. You see, if you pinch the gauge boson, you have a four Fermi interactions, and then if you pinch this, you have another four Fermi interaction. Now, then what is important here is that you see this product. If you see this product that is a product of BTS times BTD, but you have to sum over all the different up quarks that appear here. So if you sum and the masses will be equal, so if all the factors will be equal, you will obtain something that is a common factor times the product of BTS times BTD, but since, sorry, the BUS times BUD, but since the matrix is unitary, you obtain 0. So it's important for these transitions that the top quark is heavy. It's different in mass with the charm and of the up quark because that allows these transitions to be non-zero. Otherwise, they will collapse. So therefore, this was another way in which we could predict by flavor transitions that the top quark had to be heavy, and was done by processes like this that, as you can imagine, involve high precision for comparison between the rare decay process in experiment with theory. There are other more intriguing processes that are associated with a mixing of a meson and its antiparticle that are associated with CPL18 effects. But there are other four Fermi interactions that are associated with this. But I want to emphasize the role of unitarity. And unitarity is very important and can be tested. So we can take many of these processes and test the unitarity of the mass matrix because we know that the interactions depends on the matrix element of this unitary matrix. So we assume that that is true. We get the theoretical prediction for the process and we try to test relations like this, that is unitarity relations. In that case, you can form a triangle in the complex space defined by certain angles, and you can compare this, so you can get different processes, so see what are the particular products that appear in the process, relevant products, and you can project them in this particular way into these parameters. These rho and lambda parameters are simply associated with element of the matrix of the CK mass matrix. Is a particular parameterization, but what is important is that you can use these processes to test unitarity, and therefore you see many different processes, and they all converge in this vertex. So this vertex in the complex plane that simply denotes the perfect agreement of theory with experiments. So then if you get the observers, get how they depend on these parameters, and project on this particular space, you see that all of them converge, all these observers that I will not describe, converge in a single point that demonstrate the test of unitarity. Again, another success of the standard model, another precise comparison of theory and experiment. So let me go back to the Higgs. I told you that the Higgs depended logarithmically on the top quark mass, and actually on the Higgs mass. And actually, once we knew the top quark mass, we could predict the best field value for the Higgs. And from simply assuming the standard model and from the use of precision measurements, precision electronic measurements, we knew that there was an upper bound on the Higgs mass of about 200 GeV. And this upper bound was very important because guided our search for experiments. Now, the lab experiment then performed a direct search for the Higgs. This is based on processes like this, E plus E minus, then producing a Higgs in association with one of these neutral Higgs bosons. This can be searched. And then and essentially rule out all masses below 115 GeV. Now it's interesting that at the end the mass was 125 GeV. There was a small sliver of masses ruled out by the Tevatron experiment, a proton-antiproton experiment that discovered the top quark. Then was also able to test a small range of Higgs masses. But we had all these regions to test, and that was obviously successfully tested at the LHC. Now, let me say a couple of words about the LHC. The LHC program is very rich, resulting in the publication of more than 3,000 articles. This program touches all areas of particle physics, namely QCD dynamics, electronic precision measurements as the way that I described, flavor physics in the way that I described before, Higgs physics, and also the search for new particles, direct search for new particles. And we'll say a couple of words. But I think that one thing that you have to remember from my talk, if you don't remember anything else, is the fact that we are just at the start of the LHC program. So this is the integrated luminosity, the amount of data we are getting from the LHC. Right now we are here. We collected in certain units in femtobands. So then we collected about 150 in femtobands of luminosity. Then that multiplier cross-section gives the number of events that you get. And we expect that by the year 2040, we'll have more than 20 times this data. So therefore, we just started this program, and we already discovered the Higgs, and we already make, as you will see, a very significant progress. Now, we know already that by the comparison of theory and experiment, that QCD, as I said before, provides an excellent agreement with theory and experiments, and we know it in many different processes, top quark production, the production of W gauge bosons. I will comment on that later. For instance, that is, and this is computed at two-loop level, and next to in order correction. So everything is well tested, and the agreement with experiment is spectacular. Yeah. So, but all eyes are in the Higgs boson because it's newly discovered particle. The Higgs boson can be produced in different processes. One is associated with gluon fusion. Amazingly enough, although the gluon doesn't couple at 3 level to the Higgs, so this is the dominant production process that we have at the LHC. And it's mediated by the fact that via quantum corrections, so then this depends on the Higgs happening to the top quark, that is the particle that appears at the loop level. There are other processes, this one similar to the one that appears left at the Tevatron, the associated production of Higgs with a heavy gauge boson. This associated production of Higgs with the top, but this is a 3-body final state. So, and this associated production of the Higgs with jets via this process that we call it the weak boson fusion. So 2 Ws or 2 Cs that they produce a Higgs. But there is a very interesting property is that the Higgs decays into lighter particles in a way proportional to the square of the coupling of these particles. But as you remember, the coupling of these particles is proportional to mass. So essentially the Higgs decays more into more massive particles, provided this the particle masses are below mh/2. If they are above mh/2, then this rule may be violated. That's why, so for instance, so when you produce a W, so the W weighs 80 GeV, And therefore, you cannot produce two Ws on shell, two on-shell particles, if the Higgs mass is below 160 GeV. But as soon as that happens, and you open up the region of mass is about 160 GeV, suddenly WW dominates compared to BB. There is another property that is associated with the dependence of this decay with mass that also dictates why this decays become dominant all the way to very high masses and not the top, for instance. So the top that is not depicted here will open up at 350 GeV, but will remain subdominant with respect to W and C. Amazing enough. Then anyway, so but the interesting property, if you look at the mass that we finally measure, 125, the Higgs decays into many, many different final states compared to the fact that if you go to masses about 200, will only decay essentially into Z and W bosons. So therefore, we have many different ways of testing the production and decay channels of the LHC. That is fantastic. That is a gift of nature for us, because allow us to test these properties. And then in July 2012, the Higgs was discovered mostly in the Higgs decay, again, in an interesting way into photons. That is a subdominant decay channel, and into sets. So the reason why it was not discovered in the case to botons, gluons, or Ws is because it's more difficult to really measure this at the LHC. There are more backgrounds, so it's more difficult experimentally. So then now, today we have measured the Higgs production and decay in many, many different channels, and from there we get precise information of the Higgs. But to get this information, we need to know the production cross-sections at high precision. And it has been done. The letters that appear here, NNLO, is next to Lee in order in the perturbative corrections, so next to so resummation of logs. There are all sorts of refined theoretical methods. So the electroweak corrections have been included because they are not only QCD corrections, the electroweak corrections, they have been included in this calculation for the final comparison of theory and experiment. And we reach to this picture here that is simply a very simple representation of what we are observing. The comparison between the coupling that we infer from measurement to the value that we predict in standard model. And you see that these kappa values in different production modes. So these are the case of the Higgs into Z, WH boson, so the kappa T that we induce. So all these kappas we induce by an analysis of both the production and decay modes. So you see that they agree very well with the prediction of standard model that we equal to 1 in this plot.
So Carlos, you're doing well, but we are getting close to the need to stop and take final wrap-up questions. So
I need 5 minutes and I finish.
Fantastic. Thank you.
Very good. So then now another representation of this, I told you that the couplings are proportional to mass. So you can plot it in this way, and you see that indeed the couplings of particles are linear in mass. So it's in a sense the same information that we have here. Now, me-physics searches, of course, are the other avenue. Apart from precise measurement of the Higgs boson couplings, then we want to know if there's new physics. And here again is the message of precision. You know, some years ago, when we measured the WW production cross-section, there was a discrepancy between the theoretical predictions and the values that we measured. These are the theoretical predictions, these were the theoretical predictions, and these they were value measured. And that could be explained by new physics, and there were very interesting and well-motivated new physics scenarios that explain that. Now, the proper treatment of quantum correction also the reconstruction of the total cross-section from measurement. So let us today to this different picture of the same data. So, and you see that now the agreement between theory and experiment is much, much better. So, and then, so again, this exemplifies how important it is to have precise predictions. So to really not jump into conclusions prematurely of the presence of new physics. This is another example that I like, the searching for top squares, the super partners, the supersymmetric models that maybe you heard about, but the top quark in these models will have a partner that is with spin 0, and one can search for this, but the mass can be arbitrarily large. And then, what is interesting is that to make this analysis, to look for any of these new particles, you need to know the standard model production cross-sections very precisely. And that we have done. For instance, for this, the important thing is to know the top quark production cross-section very accurately. And we know it, we have nailed it, we can compare the theoretical predictions of the experiment very well, and for that we can use, for instance, to determine the background associated with the measurements. Now, there is another interesting story that these particles in these minimal models of supersymmetry predict the Higgs mass. And these predictions can be tested at high level of precision. So then this something I did work at some point, and we summarize this work in this recent article. And again, from there, you can infer that the values that we are testing right now, so are values that are maximal values of 41.2 TeV, are just the tip of the iceberg of the ones that you need to produce the observed Higgs mass in these models. So again, all these comparisons need precise calculation. So my last words are the effective field theory approach. Imagine that we cannot produce new physics directly. Can we do something similar to what we did, for instance, in flavor physics? We have some new physics at high scales, we integrate it out, we obtain some operators, and we compare the values of the coefficient of these operators due to a fit to the data with what we measure. And we obtain the values of the operator from what we measure. Ideally, in a standard model prediction, CI will be all 0. So then if there is no physics, CI will be different from 0, and we can extract it from experiment. There are certain advantages of this. This is universal. So then if you have all the operators classified, then the comparison with experiment will give you the values of these coefficients in a model-independent way. There are disadvantages. Of course, the assumption is that only the standard model are light and everything else is heavy. But we know today there is a complete classification of all the dimension 6 operators, for instance, that can appear to modify the standard model and to use to experiment. And of course, in some particular measurements, only a subset of these operators exist. But this classification exists in quite general. And as you see, it leads to many operators. Therefore, you need to reduce the number of operators for a given measurement to really extract conclusions. So my final 2 words is the following. So you remember that we talk about precision electronic data. We have also Higgs and boson production. But all of them depend on similar operators. So when we do the fit, we can combine LHC data and Higgs physics data with electronic precision data, and everything appears in the determination of these operators. And well, I will not, for lack of time, will not describe this in detail, but we have already an idea of the size and constants of operators. We don't see any particular deviation from 0 that will indicate the breakdown of the standard model so far. Then that doesn't exclude that there could be corrections to G-2 that I talked before, because the operators that G-2 affects are not these operators that I will testing here. And one can test these different models by these effective field theories methods. Okay, let me conclude and finish. The standard model provides an excellent description of all measured observables in particle physics. Its predictions have been tested at high level of precision and effort resulting from combination of hard work, of course, and novel experimental and theoretical methods, should say. A few hints of the breakdown of standard model description exist, but they will be carefully scrutinized in the coming year. And LHC is a multi-purpose experiment, so then and will collect 20 times more data in the coming years, and will provide a more accurate understanding of the Higgs sector and the physics at the West scale. Okay, thank you.
Thank you so much, Carlos. It's a great summary of so much that's been happening. Let's see if there's any questions. People should just speak up. I have a question about the LHC. If you could go back to the slide you showed of the accumulated inverse cross-section plot.
Yes. This one?
So I think my question is, I'm not tracking well what other things might be happening in terms of other accelerators. I mean, this is a 20-year projection. So this is what the LHC is doing. Could you remind us the current status of the N other huge projects that might be happening that would be relevant to to the Higgs question?
Yes. Direct observation of the Higgs so far will only come from the LHC. And therefore this is important. There are a few projects that probably are referring to. One is the International Linear Collider. That is a project that is not approved. None of the other collider projects that are interesting has been approved. But I believe that is the most realistic one. Then, although it has been in the making for many years, and I think the ball is on the Japanese government to make a decision in that direction. And then so far they have not made a final decision in this direction. So that project is interesting because will provide a complementary measure of the measurement of the Higgs couplings. So by having production of Higgs in a cleaner environment, like the one provided by plus and minus. Another project that is interesting and is similar to it is the future circular colliders. Collider electrons and positrons at energies of the order of 250 to 350 GeV. That is again an interesting project for the Higgs, but again has not been approved. There are plans both in China and at SAN in that direction. And finally, the interesting thing of those projects is that at the end of the plus and minus program, you can run protons in the same ring and have a higher energy proton collider with an energy that is not 14 TeV like the one of the LHC, but 100 TeV, so 7 times more than. That is a very interesting project, but very expensive, very long time. Finally, there is the idea of a muon collider. So one of the problems of electron colliders is that circular colliders, you cannot really accelerate the electrons at too much energy because they radiate a lot, and the radiation is reduced by mass, right? So if you have a muon, then you can increase the energy by the same size of the ring. And some people talk about having muon colliders with energies comparable to the LHC. That would be fantastic. That will really. But again, if that project happens, I believe it will take decades, not years, then to happen. So then.
Thank you. Okay. Well, thank you very much, Carlos.
No other questions? So.
I'm not sure. I'm waiting. People should just chime in. Let me look. Sometimes people are too polite and raise their hands. Usually we don't have that problem of people being too polite.
Yeah, can I ask a maybe weird question? But if there had been, it refers to the G-2 and for the muon. If there had been no, if you tried to sort of pull yourself out of the history of the events and someone were to say that there'll be an anomaly and it could be in the hadronic cross sections or in the muon. What would you have expected? Where would you expect it more to be more likely to be?
Very good. It's a good question. So then, let's say that let's compare, for instance, these lattice results I comment about with so this is an interesting question. So then the green band is associated with hadronic cross-section. So this is associated with a calculation of the hadronic bulk polarization effects in the lattice. Now, if you assume that this is true, so there will be some tension with the measurement of hadronic cross-sections at energies below 1 GeV, essentially. And the question is, how do you reconcile that? Now, if you reverse engineer, you will obtain that based on the standard model calculations of the lattice, the hadronic cross-section that is predicted in that region is higher than the one that has been measured. So therefore, it's not. So what you need is some sort of destructive interference between new physics and the standard model. If you trust this, and if you trust all the process unless there's something wrong in the way that we have been reconstructing things. So then, so I would say that if I had to bet, or if you ask me where is easier to put new physics, certainly G-2. It's very easy to put corrections to G-2 and to produce the 4.2 anomaly. So this can be done with light scalars, vector bosons, with heavy vector-like leptons, leptoquarks with supersymmetry. There is a long list of things that are not excluded by any other experiment, and I can produce the right corrections to G-2, no problem. To produce the corrections to the hadronic cross-sections, I don't know of an example. But maybe Lance can tell me if he knows.
Well, I didn't really want to say that, but it is true that if you are after this explanation, then you probably have to violate lepton universality. That is, the couplings of electrons to quarks should be somewhat different from the coupling of muons to quarks. Now, one place you can test this is in the decay of the J psi, which is the charm anti-charm, and it's been measured extremely accurately to muons and electrons, and it probably doesn't deviate enough for this, because the problem is that most of the this effect is not coming from hadrons with that heavy a mass. It's around the rho, and the data on the rho is not good enough. This is only like a 3% difference. And you can look at the rho decays to muons and electrons, but they're very rare. And so you can't claim that they're accurate. But I agree with Carlos. It's probably kind of hard to make a model that affects things that light without having it shown up at higher energies somehow. Although I still will bet money on the lattice prediction over the dispersion relations, if anybody wants to bet with me.
Yeah, you put money.
No, bottles of wine. Sorry, I didn't mean money. I only bet bottles of wine.
Right, but you believe that lattice calculation, there is a real contradiction between E plus E minus and lattice, right, at the moment.
Right.
Yeah.
Right, and in this way, I don't know. I would be rather betting that lattice is kind of underestimate its error. I mean, like that I would not believe that lattice is that accurate.
Well, I have a couple other lines of evidence. I mean, there are other lattice measurements that have larger errors, but their central values are almost always to the right of the more recent ones. And secondly, there's the tau. There's tau decays to hadrons, and they measure sort of the same thing as E plus E minus, but as Arkady knows, there are isospin corrections to that.
Yeah.
So it's not a very firm thing, but it also is on the same side. So there's some other mushy data that supports.
but E plus E minus data would be improved soon. So in this way, it would be more pronounced.
Sorry, the E plus E minus data will be improved soon?
Yes, yeah.
Which experiments are you thinking of? Bell 2?
CMD, I mean, the one.
CMD. Okay. Is that in Novosibirsk?
Yes.
Okay.
Because they kind of legislation is improved. For example, I probably mentioned before that they now separate pi from murons, which was not done before. They have kind of not model separation, but real separation. So they're thinking about considering improving, their error. I mean, yeah. So
that would be great. There's also Bell 2.
Yeah, eventually.
By the way, Bell 2 is another collider. It's a small collider, but it's a collider that's just starting to take data, and most of it is for doing flavor physics, but it can also measure this process. And Babar at SLAC and Bell 2 measure it differently from machines like CMD and Chloe, because they measure it in radiative return, where you radiate a big photon because you're at a much higher energy than where you want to measure, and it drops you down into this region.
Okay, I think we're going to need to stop here. I want to thank you, Carlos, and thank
Okay, you're welcome. Then thank you for
applause.
interaction. Then okay.
Okay, thank you. Really
Thank
appreciate
you.
it. Thanks for all the questions, everyone. Have a good rest of your Monday. Take care.
Thank you. Bye.
Bye.